In the last lecture, I had completed our discussion of spherical harmonic expansion for non-axisymmetric temperature fields, where we had got the solution for the temperature field of the form n is equal to 0 to infinity summation m equals minus n to n of a n m r power n plus alternatively can be written as summation n is equal to 0 to infinity These two expressions differ only to within a normalization constant. Okay. And I showed you that for n is equal to 0 and m is equal to 0, right, the solution corresponds to the temperature field due to a point source, okay, due to a point source that is emitting heat. Heat total energy emitted per unit time, okay, energy emitted per unit time, okay, per time is Q. Okay. Energy emitted per unit time is Q. Okay. Okay. The conservation equation for this case turns out to be K del square T plus Q delta of x is equal to 0. The temperature field is equal to Q by 4 pi K into x plus T infinity, where T infinity is the temperature far away. This solution we had got both by solving the heat conduction equation outside of a sphere of constant temperature, as well as for a point source with a delta function as the inhomogeneous term. Okay. So, if instead of at the origin, right, if we had a point source at some location x1, okay, and you were measuring the temperature field at another observation location x, right, then the temperature field will only depend upon this distance between x1 and x. Okay. Therefore, the temperature field will be equal to Q by 4 pi K into x minus x1 plus T infinity. Okay. And here I should note that x minus x1, the mod is equal to square root of x minus x1 the whole square plus y minus y1 the whole square plus z minus z1 the whole square. Okay, so that is the modulus, the distance between these two locations. Difference in x coordinate square plus difference in y coordinate square plus difference in z coordinate square, the square root of the whole thing. Okay. Okay. Now, what is the heat flux at some location? The heat flux is equal to minus K grad T. Okay. Okay. K into Ex partial by partial x plus of T. Okay, so that is the heat flux. Okay. And this is the expression for the temperature. It has 1 over square root of x1 square plus. So, if I take partial by partial x of 1 by square root of x minus x1 the whole square plus y minus y1 the whole square plus z minus z1 the whole square. That is the first term in this expansion. Okay. Okay, so this temperature I can write it as what is the derivative of this with respect to x? Okay, so this is equal to 2 into x minus x1. Okay, that is the derivative of this integrand with respect to temperature, and then I have a minus sign. Okay, 1 over r power half gives me minus half r power minus 3 by 2. So, minus 1 by 2 into x minus x1 whole power 3 by 2. Okay. So, this is basically equal to minus of x minus x1, sorry, this the minus, yeah, correct. So, this is minus of x minus x x1, okay, divided by x minus x1 whole cubed. Okay. Because this thing is just x minus x1 the whole cubed, okay, and these factors of 2 cancel out. Okay. So, based upon this, the heat flux Q is equal to minus K into minus Ex into x minus x1 by x minus x1 whole cubed, okay, minus Ey into y minus y1 Okay, note that in the denominator there are the vectors x vector minus x1 vector. Okay. Modulus of that is just equal to, okay, modulus of x vector minus x1 vector is just equal to this one. Okay. Okay, that is there in the denominator to the third power. Okay. Into q by 4 pi k. Okay. And you can see the numerator is x minus x1 into Ex plus y minus y1 into Ey plus z minus z1 into Ez. Okay. The k's will cancel out here. Okay. The plus minus and minus will give you a plus sign, and you will just get q by 4 pi into the vector x minus x1 by x minus x1 whole cubed. Okay. So, that is the heat flux, okay, at a given location x due to this single point source. Okay. So, that is the heat flux at a location x due to this single point source. Note that the temperature was given by q by 4 pi k into x minus x1. Last class I had started discussion on what happens if there are multiple sources. Okay. At locations x1, x2, x3, x4, okay, and I want the temperature at some observation point x. Okay. Then the temperature at this observation point is the sum of the temperature fields due to each of these sources. Okay. Okay. We can do that by superposition because each one is a delta function. Okay. So, I can divide the temperature field into multiple parts, each part due to one particular point source, and then add them all up. Okay. And I will get the temperature field due to these multiple sources as T is equal to Q1 by or I can take the 1 by 4 pi k outside. So, that is the temperature field due to multiple sources. A similar expression can be derived for the heat flux due to multiple sources by just adding up the heat flux due to each individual source. Okay. So, this is the solution for a point source. Okay. So, that was the term n is equal to 0, m is equal to 0 in our expansion. For n is equal to 1, m varies from -1, 0 to +1. Okay. For n is equal to 1, m varies from -1, 0 to +1. What do the temperature fields due to those represent? Okay. So, they are what are called point dipoles. Okay. So, let us consider x, y, z. Okay. A source, okay, and a sink. Okay. This is plus q and this sink is minus q, separated by a distance L. Okay. A source and sink plus and minus q separated by a distance L. Okay. So, the source location is at 0, 0, L by 2. Okay. X is equal to 0, y is equal to 0, L, z is L by 2, and the sink is at 0, 0 minus L by 2. Okay. You have the superposition of a source of strength plus q, okay, at that location, sink of strength minus q at this location. And you want to ask what is the temperature field at some observation point x due to this combination of this source and this sink. Okay. What is the temperature at some observation point in the limit as the distance between the source and sink becomes much smaller than the distance to the observation point. That is L is much L is much smaller than x. That is, the separation between the source and sink is much smaller than the distance to the observation point. Okay. So, in that limit we want to find out what is the temperature field due to this combination of one source and one sink. Okay. Temperature field can be determined by superposition q by 4 pi k into 1 by, okay. The observation point is x, okay. So, x minus 0 the whole square plus y square plus z minus L by 2 the whole square whole to the half, okay. The square root of x square plus y square plus z minus L by 2 the whole square, because the source is located at z is equal to plus L by 2. Okay. And then there is a sink minus q at 1 over x square plus y square plus z plus L by 2 the whole square whole to the half power. Okay. Now, we need to do some simplification on these terms for the case where L is much smaller than x or y or z. Okay. For the particular case where L is much smaller than x or y or z. Okay. So, x square plus y square plus z minus L by 2 the whole square whole to the half. Okay. This can be written as x square plus y square plus z square minus 2zl plus L square whole to the half. Okay. And x square plus y square plus z square is just r square. Okay. So, this can also be written as r square minus 2zl plus L square whole to the half. Okay. I can take a factor of r outside. Okay. R into 1 minus 2zl by r plus L square by r square whole to the half. 1 plus x power half is 1 minus half x plus 1 by 2 into 3 by 2 into x square and so on. Okay. So, if I do that expansion, I will get this as r into 1 minus 2 z l by I should note this as r square. Okay. Okay, because it is within a power of half. Okay. So, it should be r square. Plus L square by R square, okay, L square by 2R square. Okay, minus of half into minus half by 2 factorial into 2zl by r square the whole square. Okay. So, these are the first terms in the expansion. Okay. So, these two are the first terms. Okay. And then this is the second term, and in the second term I have neglected this L square by r square when I simplify the second term here. Okay. And once I do that, I will get this is r into 1 minus Lz by, okay, let me correct here. So, there was a mistake that has propagated down. So, let me just correct that. Okay. This is L by 2 here. Okay. This is L by 2. Okay. So, therefore, this has to be just Lz by r square, and this should be L square by 4. Okay. So, and this becomes just L square by r square and Lz by 4 r square. Okay. Okay. Whole to the half. Okay. So, in this expansion I will get Lz by 2 r square plus L square by 8 r square, okay, plus, okay, half into minus half by 2 factorial into Lz by r square the whole square. Okay. Okay. That is because we have this factor of 4 in the denominator here, and that factor came about because of L by 2. Okay. Okay. L square by 8 r square, okay, minus L square z square by 8 r power 4. Okay. So, this I can write this as 1 minus Lz by 2 r square plus, okay, L square into r square minus z square by 8 r power 4. Okay. So, that is the expansion of x square plus y square plus z minus L by 2 the whole square whole to the half power. Okay. What we have is this actually in the denominator. Okay. What we have is actually this in the denominator. Okay. So, I have to get the expansion of the inverse of that. Okay. So, therefore, x square plus y square plus z minus L by 2 the whole square whole power minus half, okay, is equal to 1 by r into 1 minus Lz by 2 r square plus L square into r square minus z square by 8 r power 4 whole inverse, okay, the inverse of this. Okay. and now you have to take 1 by 1 minus x is equal to 1 plus x square plus by 2 factorial plus etc. Okay. So, is equal to 1 by r 1 plus Lz by 2 r square, okay, minus L square into r square minus z square by 8 r power 4. Okay. That is when you take the inverse of the first two terms. Okay. And the last term 1 plus x power 1 by 1 minus x is equal to 1 plus x square by 2 factorial. Okay. Lz by 2 r square, okay, the whole square into half. Okay. And I can simplify this and I will get 1 by r into 1 plus Lz by 2 r square minus, okay, plus L square into by 8 r power 4. Okay. So, that is the expansion for x square plus y square plus z minus L by 2 the whole square. Okay. That was the first term on the left here. Okay. That was the first term on the left here. Okay. The second term has x square plus y square plus z plus L by 2 the whole square. Okay. It's the same thing except that you have to change the sign of L. Okay. It's the same expansion except that you have now to change the sign of L. 1 by r into 1 minus Lz by 2 r square plus L square into 3 by 8 r power 4. Okay. Okay, so that is the second term in the expansion. Note that I have this first term, okay, minus this second term, okay, into q by 4 pi k, right. Therefore, I have, okay, if this is term 1, if this is term 1 and this is term 2, right. Over here I have 1 minus 2, okay, here I have 1 minus 2, okay. When I subtract out the 2, 1 over r times 1 will cancel, second term will just give me Lz by r square, third term will cancel. Okay. So, therefore, I will get the temperature field as q by 4 pi k into Lz by r square. Q by 4 pi k into Lz by r square. Okay. So, this is the solution for a point dipole, okay. A source and sink separated by a distance L which is much smaller than the distance to the observation point. Okay. Note that I have QL by 4 pi k into Z by r square. Okay. I am sorry, it should be Z by r cube because I have one r outside and I have an r square inside. Okay, so let me just rewrite that as Z by r cubed. Okay. Alternatively, Z is equal to r cos theta. So, I will just get QL cos theta by 4 pi k r square. Okay. So, that is the temperature field due to a point source and a point sink. In the limit as L becomes very small, L is much smaller than the distance to the observation point. Okay. L is much smaller than the distance to the observation point. Okay. So, in the limit as L becomes very small, but Q times L is finite. Okay. So, I require that L goes to 0 but Q times L is finite. Okay, but Q times L is finite for this solution, okay, for the temperature field. Okay. Compare this with temperature, okay. T is equal to sigma n sigma m, okay, of A n m into R plus okay, P n m of cos theta e power I m phi. Okay. If we take n is equal to 1, m is equal to 0, T is equal to A 1 0 R plus B 1 0 by R square, okay, into P 1 0 of cos theta. Okay. P 1 0 of cos theta is just cos theta itself. Okay. I told you that P 0 is 1, P 1 is cos theta. So, this is just equal to cos theta, okay, okay, by R square. Okay. And you can see that this dependence cos theta by R square is the same as what we have over here. Okay. So, the temperature field due to a point dipole, that is a source and a sink separated along the z axis, okay, the temperature field due to a point dipole, that is a source and a sink separated along the z axis, is identical to the n is equal to 1, m is equal to 0 term in the expansion. The decaying term goes as 1 over r square, okay, the decaying term goes as 1 over r square, and the dependence is proportional to cos theta. Okay. What about the other two terms for n is equal to 1 and m is equal to minus 1, 0 and plus 1? We have got only m is equal to 0. What about minus 1 and plus 1? Okay. So, that one we will continue in the next lecture. Okay. I will talk a little bit about point dipoles, and then I will go to the next higher term in the expansion, which is called a point quadrupole. Okay. I will continue this in the next lecture. I will see you then.